Okay, so welcome to the lecture of this finite volume method, and what we are discussing, or rather we have discussed so far right now into the business of doing the calculation for the gradient. And gradient calculation, as we have seen our previous lectures, we have two approaches. One is the using compact stencil, other one is the extended stencil. And in the last lecture we have discussed the calculation procedure using the compact stencil. So, now you will move to that today on the using the so essentially what we are doing, the gradient which is for a particular cell is represented as summation over all the faces, and so this is what we are into the business. So, essentially that is the gradient calculation that we are trying to do. So, that is our objective. Now, once you are trying to do this gradient calculation, there are ways how we can do that, and especially when you move to the non-orthogonal system, you come across the cross diffusion term. So, gradient calculation becomes very important in the sense that in the cross diffusion term cannot be evaluated using the nodal values. Now, how do you define your discretized stencil? That leads to two approaches. One is the using some sort of a compact stencil, and where what you do that you have a correction term for your flux or the surface flux, which is like Gc phi c minus 1 by Gc phi f, where C is the particular element that one is concerned of calculating the. So, essentially if you quickly have a diagram like a particular cell, this is C what we are interested, and this is F, and this is the connecting line between C and F. So, and this is the phase F. So, calculation of the phase values which are interpolated using this formula, and Gc actually is nothing but your geometric weighting factor. So, this, and how to calculate this surface flux phi f or the corrected flux and the Gc, for that there are different options. So, we have discussed three options: option 1, option 2 and option 3. So, that is what we have essentially done till the last class. Now, what we want to see using is the compact stencil. We have looked at it. So, now we want to look at is the extended stencil. So, that means which clearly give us an idea the cell which would be calculated, it is not going to be connected with an immediate cell like this, rather it would be connected with some other surroundings element. So, to do that, let us look at this particular stencil. So, look at this 2D stencil. Now, why we call it extended? Because there are F1, F2, F3, F4, these all are connected. So, you can see the cells contributing to a particular node, which is node for the weighted average. So, being said that, you can see the node N1 which is getting contribution, since that node is common to three different elements like F1, F2, F3. So, that gets the contribution from all three elements. Similarly, if you look at the node N2, the N2 is getting contribution from all three elements like F2, F3, F4, and connections between F is the phase between N1 and N2 or the connecting node between N1 and N2. Now what we need to calculate is the value of phi F. So what we are interested finding this value, finding the value of phi at the phase F, which can be computed as the mean of the values at the vertices N1 and N2. So this essentially necessitates the estimation of the properties at the vertices. So far we have been dealing with the system where we all concerned about the values which are available at the cell center. Now here, while you are trying to calculate this surface flux, you need to get an information at the nodal point. So the properties at a vertex node are calculated using this weighted average. So this is some sort of a weighted average which is used. Now how we take the weighted average? Because we take some sort of a inverse distance function to calculate this kind of weighted average. So in that case, when you calculate the phi n, which can be expressed as the summation over k equals to 1 to NBN phi Fk divided by Rn minus Rfk, and denominator, this is k equals to 1 to NBN 1 divided by Rn minus Rfk. So here n stands for the vertex node, Fk neighboring cell node, NBN stands for the total number of cell nodes surrounding the vertex node. So surrounding the vertex node. So essentially you get all this information and vertex node n, and then we have a distance function Rn minus Rfk. So that stands for the distance from the vertex node to the centroid of the neighboring cells. So that is what it gets you back. So you have all the information, you have the vertex node, you have the total number of nodes, you have the neighboring cell node, then you have the distance from the vertex node to the centroid, and then you can get some sort of a distance, average distance calculation. Once the phi n at the vertices are found, then at the face you can find out the phi f as phi n1 plus phi n2 divided by 2. So using this sort of a inverse distance calculation at n1 and n2 we can find out, and once we find out n1 and n2, the surface flux or the variable could be obtained using some sort of a arithmetic mean, and similarly the gradient would be calculated 1 by Vc summation of F NBC phi f SF, which is 1 by Vc summation of, then we get phi n1 plus phi n2 divided by 2 at F SF. So when you go to 3D system, the calculations are little bit involved, but it goes in the similar fashion, and there you can also go across all the nodes or the vertex node and can find out. Now, in this particular approach, the information from the wrong side of the cell also contributes to the weighted average. So, if you look at this picture, it may possible that the cells which are actually sitting on the wrong side, they can also contribute to this weighted average, to the conserved variables. So, this can be overcome by using some sort of an upwind biased gradient, and the higher order calculation based on the upwind biased gradients have both the memory overhead. So, essentially there could be some, you can note, contribution to the weighted average from wrong cells. That is possible. If that happens, it can be overcome by some upwind biased gradients calculation. And if you use some sort of an higher order upwind biased calculation, the computing overhead also goes up. So, the computing overhead also goes up. So, that is little bit involved, and now if you move to 2D to 3D, that becomes bit tricky. Now, so that is how one can use the compact stencil and calculate the flux variable at the face. Now, we can move to the another option, is that least square gradient calculation. So, this is another option, and least square method it offer actually more flexibility. So, it offers more flexibility with the regard to the order of accuracy. So, order of accuracy is also slightly better or higher compared to other. And in the least square method, what happens, the divergent based gradient can be recovered as a special case. So, that is one of the advantage of this least square method. And the flexibility, when we talk about the flexibility, it brings some flexibility to a table, it actually comes at certain cost. So, as proper weighting is needed for the stencil terms, the computation of weights add to some sort of an computational cost. So, this is getting hit by some sort of an computational overhead. So, once it offers you better flexibility or slightly better accuracy, it also comes with some sort of an computational overhead. So, it is not that straightforward that you can get everything together in your plate and get these things. So, let us look at this particular stencil and the change in the, so here the cell which are concerned cell is cell C, and these are the all neighboring cell, and then we can have an exchange between C and F. So, this could be F1, F2 like that, and this we need to get the information of phi C, phi F and all this. So, to calculate the gradient, and so this with shows the schematic with the neighboring cells of this. Now, how do we obtain that phi F? Phi F it obtained at the using the value of phi C plus delta phi C dot RF minus RC, which is essentially the RCF. Now, the thing is that unless the solution field is linear, the cell gradient cannot be exact, because C has more neighbors than the gradient vector has components. So, every time you get this calculation of the distance with the gradient vector, now C has the number of more neighbors. So, in least square method, a gradient essentially is going to be computed by an optimization procedure. So, you calculate this gradient by an optimization procedure. So, let us find the minimum of the function is GC, and GC can be defined as summation k equals to 1 to NBC weight factor Wk phi Fk minus phi C plus delta phi C dot RCFK. So, this is square. Now, if I expand this one slightly more, so I will get k equals to this, I have this Wk, then I can write delta phi k minus delta xk del phi by del x at C. So, that is one component, del yk del phi by del y C plus del zk del phi by del z C. So, that is the term, and then you get the closure of this bracket, which is going to be the square, and closure of the other one, where your Wk is some weighting factor. So, using that you get this term. Now, the other terms which are involved there, delta phi k is phi Fk minus phi C, delta xk is R Cfk dot I, delta yk equals to R Cfk dot j, and delta zk is R Cfk dot k. So, Ijk. Now, the minimization of this function can be obtained, minimization of GC can be obtained by enforcing some condition. The condition is that del del GC of del phi by del x equals to del GC of del phi by del y equals to del GC of del phi by del z. These are all 0. So, once you get this minimization function or the mathematics, which will actually get you back some sort of an involved mathematical expression k1 to NBC, which will get you 2 Wk delta xk minus delta phi k plus delta xk del phi by del x C, delta yk del phi by del y C plus delta zk del phi by del z C, which is 0, number 1. So, that comes from the first expression. Second expression gets you back the similar expression, but it is on yk. So, it will be delta phi k plus delta xk del phi by del x C plus delta yk del phi by del y C plus delta zk del phi by del z C. So, that gets you the second one, and the third condition will get you another condition or expression on delta zk. So, which is phi k del phi by del x C plus del phi by del y C So, one can take the derivative of the previous expression and can obtain all these conditions. So, you get from here you get all these 3 conditions. So, each of them corresponding to the first one actually corresponding to this derivative, the second one corresponding to this derivative, third one corresponding to this derivative. So, you obtain these conditions which one can write in some sort of a matrix form, and if you write in some sort of a matrix form, this will look like summation k equals to 1 to NBC Wk delta xk that is first term, k equals to 1 to NBC Wk delta yk xk delta yk, third term k equals to 1 to NBC Wk delta xk delta yk. So, that is what, and the second term will contribute to Wk delta yk xk, and similarly you get Wk delta yk delta yk, and the third one is k equals to 1 to NBC Wk delta yk delta zk. This is k equals to Wk delta zk delta xk Wk zk yk 1 2, and you get on the factor which is getting multiplied is that del phi by del c at c, del phi by del y at c, del phi by del z at c, which is equal to my another vector which is k equals to 1 to NBC Wk delta xk delta phi k. Similarly, k equals to 1 to Wk delta yk delta phi k, k equals to 1 to NBC Wk zk phi k. So, you gotten essentially the matrix form. So, this is the matrix form of the previous equation. Now, how do you find out the solution to this particular equation? So, basically solution, obviously the solution exists if the matrix is not, if this matrix is not singular. So, that means this has a nice condition, or it has to have a non-singular system so that it can have. Then also the choice of Wk. So, that is another factor. So, choice of Wk is also very important, because that will essentially to some extent or rather partially contribute the convergence of this system. So, for example, if Wk is chosen to be 1 for all the neighbors of C, then all neighboring points will have the same weight in computational of the gradient, irrespective of whether they are near or far from point C. So, that is one problem. Actually, points that are further from C will have a more important influences at the error function, which will be more affected by their error. So, this is a very important or crucial element in this particular matrix, because that has lot of impact. So, if you go back to this cell, now since it is taking the neighboring cells information, if for certain values of Wk it may have possibly have the farthest cell has lot of influence on this approximation, and that can lead to some sort of an error. Or alternatively, one can have some alternative choice for Wk. So, that one which something which has been used and can be obtained is that Wk could be some sort of a inverse distance function, r Fk minus Rc, which is going to be should be del x Fk square, del y Fk square, del z Fk square. So, that way one can actually estimate the Wk. Okay. So, other option is that one can also use Wk as an inverse distance of power n, where n could be 1, 2, 3 and so on. So, it is also possible not taking the direct inverse, you can take in power of that inverse or with some kind of things. Now, as mentioned, the divergence based gradients is a special case of the least square formulation. So, one can show that. So, what we have said that divergence based gradient is essentially a special case of the least square formulation. So, the formulation that we have for the least square approximation, one can also obtain the divergence based gradient, and we can see that. So, thank you. We will discuss our other things in the next lecture.